Think back to the last time you used flashcards to study for a test. You look at a card, make a guess, check the answer, and try again for the next one. This loop of guessing, failing, and adjusting your memory is exactly how modern computers learn to handle complex tasks. Meet Pip. He's preparing for a toy sorting test, and he's going to help us understand how a computer's brain actually processes information. To pass this test, Pip uses a specific digital setup called an artificial neural network. Artificial intelligence doesn't require a human to program every single answer in advance. Instead, we build a system that can learn through constant practice. This diagram shows the structure of a standard neural network. It is organized into columns called layers. Think of this as Pip's Firefly team. Each acts as a single neuron, connected by glowing strings. The front input layer looks at raw flashcard details. They send signals to the middle hidden layer to process data. Finally, the output layer holds up the team's final guess. Even the most advanced AI models are just layers of simple messengers working together to reach a single conclusion. Let's watch Pip's first attempt at identifying a toy. The moment he sees the flashcard, his Firefly team springs into action. That's the forward pass. A firefly in the front row pulls a string, passing a physical signal to the middle row, which then yanks strings to the back. Since the network is brand new, the connections are random and jumbled. The output firefly holds up a sign for bone when the picture is actually a ball. To fix this, we measure the loss. This is a mathematical value that tells the computer exactly how far off its prediction was from the truth. Making a wrong guess is a necessary first step. An AI system cannot improve until it measures the size of its own failure. But with so many fireflies, how does the team know which specific strings caused the wrong answer? They use backpropagation. The error signal moves backward from the output firefly, tracing the path to find which connections to blame. During this backward pass, fireflies adjust the tension, or weights, on their strings. They loosen bad connections and tighten ones leading to the right answer. One card isn't enough to learn the pattern. Pip needs to process the entire stack of flashcards to understand what makes a ball a ball. When the network finishes guessing every card in the stack and adjusts all the strings, we call that one epoch. Real networks repeat this loop thousands of times, guessing, measuring the loss, and refining the connections. This transition from failure to success happens through constant tiny adjustments to the strings, turning a series of mistakes into a reliable system. Finally, it's test day. We place a brand new toy in front of Pip, one he has never seen before. This phase is called evaluation. Testing Pip on a new toy proves he recognizes the general traits of a ball rather than only knowing the specific cards he saw during practice. During this final forward pass, the tuned strings pull exactly the right way. The signals flow through the network without hesitation. The signal reaches the end, and the output firefly confidently identifies the new toy as ball. This success is a prediction. The trained AI can now take in new information from the real world and categorize it accurately. Neural networks succeed because they don't rely on a list of rules written by humans. They develop their own logic by refining thousands of connections until they can solve the problem on their own.